Hi everyone, my name is Dr. Chin and I'm making a quick tutorial video on how to fit an unconditional growth model to your dataset. If you haven't already watched my previous video, Chapter 4B, fitting an unconditional means model, I would encourage you to watch the video first before watching this model, although I'll also provide a quick overview on what we did before just to give you some context. Parts of this presentation is adapted from the PowerPoint slides provided by Singer and Willett in 2003. So this is the website where you can get those original PowerPoint presentations. And I'm also taking the R syntax for this tutorial from the blog page by Clayford. And so this is where, this is the website in which I got the R syntax for this particular tutorial. So let's briefly review what we did in the previous video when we're fitting an unconditional means model. With the unconditional means model, we basically are doing this because we want to partition the total amount of variation in alcohol use scores into between person variance and within person variance. And to do this is very simple. We basically are saying that the estimated alcohol use for person I at outcome J is a function of the grand mean across individuals and across occasions, plus the between person deviations from this grand mean and the within person deviation from this grand mean as well. And so when we fit this model, we get the fixed effect over here. So this represents the grand mean across individuals and occasions. And more importantly, we get an estimate of the between person variance and the within person variance, 0.564 and 0.562. Why do we do this? The reason why we do this is because the estimated between person variance and the within person variance gives us a sense of, how much variation at level 2 can we try to account for more with adding more predictors at level 2, and how much more predictors can we add into level 1 to be able to account for within person variability. In this case, from the unconditional means model, we can see that both the estimated between and within person variance, they're both statistically significant, suggesting that we can probably add in more level 2 and level 1 predictors, so between person and within person predictors, to be able to do a better job of accounting for the total amount of variation in our alcohol use scores. In fact, by calculating the intraclass correlation, which is basically the it is the between person variance divided by the between person variance plus within person variance. This gives us an estimated 50% of the total variation in alcohol use that is attributable to differences between adolescents. And so with that, we are going to try to add in more predictors. Specifically, if we want to call this a model of change, we need to include time, obviously. And this is the next step. And this is what we're going to focus on in this particular video so that we can answer the question of what role does time play in being able to predict alcohol use scores across time. So this is the model that we're going to be working with. And we've got the usual similar components of the multi-level model. We've got the level 1 submodel, level 2 submodel, and the composite model. The composite model is basically a combination of level 2 and level 1 models. This is basically what happens if we were to define pi subscript 0i and pi subscript 1i with these level 2 parameters over here into the level 1 submodel. You multiply them and expand them, you basically get the composite model. So let's walk through this really quickly because I'm hoping this will make sense to you in terms of what are the exact parameters that we're working with over here. Remember, this is the unconditional growth model. This is our baseline model for change over time. We're probably going to compare other more complicated multi-level models for change with this baseline model. So it's important that we understand what this baseline model is. So at the level 1 model, the estimated alcohol use for person I at time point J is a function of two fixed effects. We've got pi subscript 0i, which is the estimated true intercept for the individual change trajectory. And we've got pi subscript 1i, which is the estimated true change in alcohol use per unit of time for the individual. Now, of course, there's going to be some deviations from each person's observed alcohol use score from this estimated true change trajectory, and that is captured by lowercase epsilon subscript ij, which is the deviation of each person's observed alcohol use score from the estimated true change trajectory. And we assume that epsilon subscript ij is normally distributed, it has a mean of 0, and has a specific variance called sigma squared with subscript e. Now, at the level 2 submodel, those two fixed effects that we just talked about over here, pi subscript 0i and pi subscript 1i, these are now outcomes at the level 2 model. So pi subscript 0i, which again, this is the estimated true intercept of the individual change directory for each person. This is going to be a function of gamma subscript 0, Gamma subscript 0 represents the estimated intercept of the population average change trajectory plus deviations from this population average change trajectory. This is captured by zeta subscript 0i. Pi subscript 1i, which is the estimated true change in alcohol use per unit of time for the individual's change directory, is a function of gamma subscript 10, which is the estimated slope of the population average change directory plus deviations from this estimated slope of the population average change directory, covered by zeta subscript 1i. And we assume that each of these residual components that they are both normally distributed, and they both have a mean of 0. They have specific variance estimates for the initial status and for slope, and there is some type of covariation between these two variants. So the composite model, naturally, is going to be a combination of the level 1 and level 2 submodels, which is basically going to say that each individual's observed alcohol score is a function of gamma subscript 0. Remember, gamma subscript 0 is the estimated intercept of the population average change directory plus gamma subscript 10. This represents the estimated slope of the population average change directory multiplied by time plus these stochastic components over here, or the composite residual from the level 1 and level 2 submodels. So zeta subscript 0i, this represents deviations from the estimated intercept for the population average change trajectory, and zeta subscript 1i represent deviations from the estimated slope for the population average change trajectory multiplied by time. And then we've got the level 1 residual as well, which represents the deviations of each individual's observed score from the estimated true score based on the fixed effects of the level 1 submodel. So this table over here shows the results of fitting this unconditional growth model. We can see that the estimated intercept of the population average change directory is 0.651. This basically represents alcohol use scores at time point 1, okay? Or if you may recall, the authors did say that they actually did a transformation of the alcohol use variable to help meet some linear assumptions. So it's actually technically the square root of alcohol use scores at time point 1. But just for the sake of simplicity of interpretation, let's just say that gamma 0 over here, or 0.651, is the alcohol use scores when all participants are at time point 1, which is age 14. The slope of the population average change trajectory is shown by gamma subscript 10. This is actually 0.271. So this represents the change in the transformed alcohol use scores whenever time increases by 1 unit. So the composite model, in terms of writing it out, if you're just focusing on the fixed effects, is basically going to be, and this should look very similar to any type of y equals to mx plus c type of formula. You've got the intercept, you've got the slope, and this is a function of time. It is h minus 14 because for this For example, the authors decided to use a certain variable of time so that the intercept represents alcohol use when time equals to 14 years old, as opposed to, when the participants are 0 years old, because that wouldn't make too much sense. So this represents the fixed effects. We're going to try to reproduce this graph for you over here. This shows you how much alcohol use changes across time. Now let's take a closer look at the variance components over here, because the variance components are actually super interesting because it will help us. It's basically going to be the yardstick for us to compare all other subsequent models to whenever we're adding, more level 1 and level 2 submodel predictors. So we can calculate the proportional reduction in the level 1 variance component because we added time at the level 1 submodel by using this formula over here. We basically take the amount of within person variation from model A, which is the unconditional means model, and we subtract from that the amount of leftover within person variation from model B, divided by the original total amount of within person variation. And when we do that, we actually get 0.40, which means that 40% of the within person variation in alcohol use is associated with time in a linear sense. So that's good news. That means that it makes sense for us to add time as a level 1 predictor. The other thing which I want to point out to you as well is that we can use this generic model, the pseudo R-squared generic model, to calculate how well are our future subsequent models in adding more level 2 predictors compared to our unconditional growth model. Because remember, with our unconditional growth model, we actually don't have any between person or level 2 predictors. And so this is kind of be our yardstick for us to know if subsequent models are going to do a good job of being able to reduce the amount of level 2 residual variance when we add those level 2 predictors. So on that note, notice that at the level 2 model, you always have 2 level 2 variance components, which is sigma squared subscript I. This quantifies the variance of deviations resulting from each individual's change trajectory's intercept from the population's average change trajectory intercept. And then we've got sigma squared subscript 1, which quantifies the variance of deviations resulting from the individual's change trajectory slope from the population's average change trajectory slope. Sorry about that. So for each of these residuals, whether that be sigma squared subscript 0 or sigma squared subscript 1, you can calculate a pseudo R-squared based on the generic model over here to estimate the percent of between person variation in alcohol use that is associated with the addition of 2 or more level 2 predictors. So if you wanted to calculate a pseudo R-squared for, say, for the in terms of the variance for the intercept, we basically put in the variance for the intercept at the level 2 submodel minus the variance for the intercept or the level 2 submodel for future more complex multi-level models of change, and divide that by the level 2 residual for the intercept. So these are the results published in your textbook. We've got the fixed effects at the top. We've got the variance components at the bottom. We're going to recreate this in our studio in just a little bit. I'm just going to show you where how these numbers here match up with that. So let me walk you through our studio really quick to show you how to fit this unconditional growth model. So first of all, you want to load the library. It's LME4. And we are going to use the LMER function. Let's call this model.b1. Use which is a centered variable for time. Let's go 14. So this basically designates that, so the plus and then in parentheses H14 ID, this is stating that this is a within subjects design and that the random coefficients can be correlated at various data collection waves here. We're going to use alcohol 1 as the data set and turn off restricted maximum likelihood as the estimator, which means that it will use full maximum likelihood. That's right. And let's get the parameter estimates. As you can see here, we've got the fixed effects, we've got the random effects. I've copied and pasted this into the PowerPoint slides. I'm going to show you what's what. So the fixed effects underneath for this row intercept here, this represents the estimated intercept of the population average change trajectory. This one represents the estimated slope of the population average change trajectory. This one over here represents the variance of deviations resulting from each individual's change trajectory's intercept from the population's average change trajectory intercept. This represents the variance of deviations resulting from each individual's change trajectory slope from the population's average change trajectory slope. This one over here represents the epsilon subscript ij, which is basically the deviation of each individual's observed score from the estimated true score based on the fixed effects of the level 1 submodel. So back to this again, remember this, this represents the fixed effects of the unconditional growth model, and we got this graph. So we can recreate this in RStudio. So let's go ahead and do that. To do that, it's really simple. First of all, we need to extract the fixed effects estimates. So let's call this fixed effects.b. I'm going to use the fixef function to extract the fixed effects from model B1, which is the model that we just ran just now. Oops, sorry. And we're going to create a function based on the extracted fixed effects for the 3 time points. One means we want to pool the intercept. Three time points, multiply that by the fixed effects, the slope, basically. T. It's going to be able to pool the slope for the population average change trajectory. And let's plot the graph. B is the function that we just created just now. So set the limits of the y-axis. Use. Title. Unconditional. Type B is basically just a type of plot that we're going to be calling from the plot function. So this is the plot. So with the y-axis, sorry, x-axis representing time, and the y-axis showing the predicted alcohol use based on this particular function here, the fixed effects of 0.65 plus 0.27 multiplied by h. So what do these unconditional models, so this includes the unconditional means model and the unconditional growth model. Well, from the unconditional means model, we talked about how once we partition the total amount of variation into between and within person variance, we find that about half of the total variation in alcohol use is attributable to differences between teens. And then from the unconditional growth model, we found out that 40% of the within teen variation in alcohol use is explained by time. And that there is, so basically all that to say that I think it's worth exploring level 1 and level 2 predictors, although in the examples in this chapter, we'll mostly be exploring level 2 predictors, and in chapter 5, we'll start talking about including level 1 predictors. So how do you build from here on out? Now that you've got your unconditional growth model, this is the basics over here. And you've got a sense of how much of the variance is accounted for by between and within person people. You want to use your intuition and skills that you have from the cross-sectional world. You can add in each predictor separately, or you can add in simultaneously. Usually, at the very least, most people will fit the unconditional means followed by the unconditional growth, and then they'll usually go on to their final model. But you may find, just as how we might show in subsequent examples after this, that you may decide to tweak your models depending on the statistical significance of your fixed effects and stochastic effects. Each of the level 2 outcomes, so we're talking about the individual growth parameters, each of them can be related separately to different level 2 predictors, and the individual growth parameters themselves may also interact together with other level 1 predictors. There are two kinds of effects that are being modeled in a multi-level model of change. We've got the fixed effects and we've got the variance components. And so just sort of remember that as you think about what goes into your multi-level model of change. Typically, the fixed effects are what are the graph that we should think about visually when in trying to describe the relationship between our predictors and our outcomes. And the variance components, which is basically the leftover amount of variability that is not accounted for by our level 1 and level 2 predictors. That's kind of interesting too, especially if we're using that to help lead us in the direction to figure out if we should add more level 1 or level 2 predictors. So in subsequent models, we're actually going to fit model C. So this is when we're going to add in a dichotomous variable of whether you are a child of a parent who is an alcoholic, yes or no. And then we're going to add in peer. This is model D, where we are going to add in the influence of your friends, what proportion of them is actually drinking on a regular basis. And then model E is basically going to be a revision of model D because there's a non-significant effect of COA on change. So in subsequent videos, we're going to fit these models over here, but the two basic models that you should always fit in a multi-level model change is the unconditional means model and the unconditional growth model. So I hope this was helpful. Let me know if you have questions.